Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 49 today and we are discussing about a thin layer of adhesive that is present at the back of a scotch tape. And we discussed about the peel experiment in lecture 47, and after that we discussed about some instabilities that happens at the contact of an adherent, a flexible adherent and a thin elastic film bonded to a rigid substrate. So, it was something like this, that we have this elastic adhesive film, it was bonded to this rigid substrate, and then a flexible adherent plate was brought in contact with it, and there was a spacer here, and there is a, because of adhesion, this plate comes in contact with this film, and then there is a equilibrium that is attained between the forces, and the contact line becomes static at a location, and at the contact line, along the contact line, for depending on some conditions, we saw some instability patterns like that. A slightly different experiment, we observed this kind of cavities, isotropic instability, and then when we have some kind of relative rotational motion between an adherent plate and an elastic adhesive, we get this kind of ring-like structure. So, we discussed these things in lecture 48, and before that in lecture 47 we discussed about the peeling experiment. Now, in both these cases, you see that there is adherent plate which actually bends, but we have not considered here bending. So far we have not considered the bending of an adherent plate. In fact, in the peel experiment also there is a backing layer on which the glue remains bonded, and so that backing layer also bends. We didn't discuss about that. So today what I am going to discuss about can be seen in this book by Landau and Lipschitz, volume 7, on theory of elasticity. So in a sense, what I am going to talk about today is bending of a thin plate. So basically we have this very thin plate H. So H is much smaller than with respect to the spatial length scale, that is the L. So it goes from, let us say, minus L by 2 to plus L by 2, and then we apply some kind of torque over here, or let us say we apply some kind of force. The force can be applied let us say in a distributed manner or in a concentrated manner, and then this particular plate that bends, and the bending can be in both about both the y axis and the x axis. So here the picture, this shows that this is the y axis. So the bending here is about the y axis, and bending occurs along the, so there is a displacement, and the displacement occurs along the z axis over here. So this is the x axis and this is the z axis, and this bending happens along the y axis, and because of that what happens is something like this. If I magnify this cross section, so this is the cross section over here, and there is a neutral axis. So neutral axis means that when you bend, so this portion goes up, something like that. So in this region, the inner side, this particular surface that becomes compressed, and the outer surface, it becomes stretched. So there is a tensile compressive load over here and tensile load over here, and that becomes 0. So that becomes 0 at the neutral axis. So the neutral plane, there is no tension, no compression. So this is called the neutral plane, not axis, neutral plane. So it is like that. Now this neutral plane, what is the deformation at the neutral plane? Vertical deformation. That is this zeta that we have written over here. So W is 0 means over here is neutral plane, basically a neutral surface or neutral plane. This superscript 0 means this is neutral surface or neutral plane, and there is a vertical displacement of this neutral plane because of this bending, as I showed here. So this is given as zeta, and this zeta will depend upon x and y depending upon how it bends. So we will we will derive the equations for bending for both about the x axis and y axis, and then we will take up some special case for bending only about the y axis. We will see it in soon. So it is like this. Now, so since the bending is small, the normal vector to any point on the bent plane is along the z axis. So what it means is that this is become bending. So, the normal plane about on any point will be like this along this direction, but since the bending is small and indeed bending the kind of bending that you are considering is very small. So, therefore, this axis, this direction, this n vector, let us say that lies along the z vector. Okay. So, that is what is being said. So, this happens because the bending is very small. Then since the plate is thin, it bends very easily, so that very small amount of force needs to be applied on the surface of the plate, and it is a plane stress problem. So, this is very thin sheet. Okay. Most of the stresses remain along in the plane only, and so this is a plane stress problem. Remember that at the beginning we had discussed about plane strain approximation and the plane stress approximation. So, this is a plane stress problem. So, that these stresses which acts on this plane that is perpendicular to the z axis, these are actually equal to 0. So, this is this stress that acts along the x axis on the plane that is perpendicular to the z axis. This is stress along the y axis, but acts on the plane perpendicular to the z axis, and here zz is the stress that acts along the z axis, but on a plane that is perpendicular to the z axis. So, these are all equal to 0. Now, sigma xz is equal to 0. So, what it means is this is mu into del u by del z plus del w by del x, that is equal to 0, and del sigma yz becoming equal to 0. So, here this means, let me complete it. So, del u by del z will be equal to minus of del w by del x, and sigma this is about sigma xj becoming equal to 0. Now, sigma yz becoming equal to 0, what it will mean is this is mu into del v, let us say del z plus del w by del y, okay. This is equal to 0. So, what it means is equal to del v by del z, okay, is equal to minus of del w by del y. Now, remember that this w is the displacement along the z axis, and at the neutral plane this displacement was given as this zeta xy, and this neutral plane. So, the zeta will be same for all the points along the z axis. So, therefore, what we will soon have, what we will show is that this zeta is equal to w is equal to zeta xy. So, let me write it over here. So, w equal to zeta x and y, and so therefore, this is equal to minus of del square zeta by del x square, and this is equal to minus of del square zeta by del y square, like that. And then we have got sigma zz equal to 0. So, sigma zz, the formula will be given as this E by 1 plus sigma into 1 minus 2 sigma, and here it is 1 minus sigma into E zz plus sigma into E xx plus ay. So, here E zz, so that is equal to minus of sigma by 1 minus sigma into E xx plus E yy, and so that is equal to minus of sigma by 1 minus sigma del u by del x. Now, what is u? U we have I can obtain from here. So, here remember that zeta is a function of x and y. So, therefore, from here we can write here that u is equal to minus of z del square zeta by del x square, and from here v equal to minus of z del square zeta by del y square. So, del u by del x, therefore, it is E xx, right. So, del u by del x, so it is del w del x, yeah, del square zeta by, this is del zeta by del x. So, del u by del x, therefore, del u by del x will be equal to minus of z del square zeta by del x square, and here del v by del y is equal to minus of z del square zeta by del y square. So, this is it. So, now over here E xx is del u by del x, it is actually del u by del x plus it is del v by del y. So, del u by del x is, I have derived it over here. So, let us substitute over here. So, it will be minus plus here, and let us say del u by del x So it is del square zeta by del x square plus del square zeta by del y square, right. So EZZ equal to this. So EZZ is the strain along the z direction. So this is here. So here it is. So like that. So we have already derived it. And so therefore we can actually estimate what will be the strain energy density function. So remember that this particular expression I have given it in lecture 3 or lecture 4, okay, where this lambda you have the expression of that was also given, mu is shear modulus was given. So this is the Lamè's constant. So now Exx plus Eyy plus Ezz, and then you have to estimate this quantity. So we will like to do that. So Exx we just derived it to be minus Ex minus z into, so it was minus z into del square zeta by del x square minus z del square zeta by del y square minus minus plus sigma by 1 minus sigma into z into del square, this is Ezz. So it is del square zeta by del x square plus del square zeta by del y square. So Ezz is this. So therefore this is equal to, so sigma x Exx is equal to minus z, e minus z here, that's fine, and this is this. So this is equal to so let's say z into this is sigma by 1 minus sigma minus 1, and this is equal to del square sigma by del x square, and this should be equal to actually del square sigma by del y square as well. So this will be equal to minus z into 1 minus sigma, and so it is 1 minus 2 sigma into del square z by del x square plus del square z by del y square, like this. It is minus 2 sigma, so minus z 1 minus 2, that is fine. So Exx plus Eyy plus Zz we have just obtained, and then you have to obtain Exx square plus Eyy square plus Ezz square and Exy square and Eyz square and Ezx square. So now these quantities Eyz square we can find it to be 0, because this this is 0, this sigma yz and sigma xz is equal to 0. So sigma xz and sigma yz is equal to 0. So for this quantity and this quantity, these are equal to 0. So therefore over here, okay, these two quantities are equal to 0. So we have to worry about this quantity, and sigma is z0 is equal to 0. So this is not 0. So yeah, so this is okay. So now let us estimate that. So Exx square plus Eyy square plus Ezz square. So here let us do that. So Exx square is equal to, okay, mu into this, so mu and Ex square, so g square, okay, and Ex square is del square zeta by del x square. Remember this is a function of x and y. Every time I am not going to write it, square, and then plus this is a yy square. So this is also yy square here. So del square zeta by del y square and then plus this is Ezz square. So it is sigma by 1 minus sigma whole square, and here it is del square zeta by del x square plus del square zeta by del y square. Yeah, this is correct. And then we have got this xy, you will be able to find it to be like this only. So 2 and Exy square, so it will be del square zeta by del x del y square, like this. So this we have to find out now. So here mu into z square, and this is del square zeta by del x square, and this is del square zeta by del y square, both are whole square here. So let us do it like this. Let us write it to be del square zeta by del x square plus del square zeta by del y square whole square minus 2, and here it is del square zeta by del x square into del square zeta by del y square, okay, and then here plus this is sigma by 1 minus sigma whole square into this square plus 2, here it is del square zeta by del x del y square. So now we can combine this quantity. So here it is the same thing here. So we can actually do that, mu z square into this is 1, this will be let me 1 minus sigma whole square. So it is 1 minus 2 sigma plus sigma square. So let us write it like this, 1 plus this is sigma square by 1 minus sigma whole square, and this is del square zeta by del x square plus del square zeta by del y square whole square minus 2, this is del square zeta by del x square into del square zeta by del y square plus 2, this is del square zeta by del x del y whole square. So this is about mu into this, and here we have obtained lambda into this exx plus eyy plus ezz whole square is equal to, here it is half, so half here, and lambda means this quantity, and then this z square, so the lambda means this, that is correct, and then this there, and then this exx plus eyy plus ezz whole square, so this will be this quantity whole square. So all these things come out to be something like this, which is fine. Now we add up both the quantities. So we have to add up this quantity over here and then this quantity over here. So we have to add up. So if you add up, so actually what we are adding up is in essence these two quantities, you see. So this part we have to add up over here. So we do that. So this will be equal to E z square by 2 into 1 plus sigma. So this comes because mu is in place of mu, we are writing this E z square plus 1 plus sigma here. So E z square plus 1 plus 2 sigma. So here you have got this part also common, so we can take it inside. So here it will come out to be therefore del square. So it will come out to be, yeah, so del square zeta by del x square plus it will be del square zeta by del y square whole square, and then plus, so if you add this, so what will come out to be, so let us do it separately. So it is sigma by 1 minus sigma whole square plus sigma into 1 minus 2 sigma by 1 minus sigma whole square. So it will be 1 minus sigma whole square, and this is sigma square plus this is sigma minus 2 sigma square. So it is sigma into 1 minus sigma. So it is sigma minus sigma square. So sigma into 1 minus sigma by 1 minus sigma whole square. So it is 1 minus sigma. That's what it comes out to be. So here it will be sigma by 1 minus sigma. I am not deleting it. Okay, you can do it on your own also, I know. So here therefore it will be sigma into 1 minus sigma. So sigma into 1 minus sigma, okay, into this is del square zeta by del x square plus del square zeta by del y square, this is whole square, plus just have this quantity. So this is 2 into del square zeta by del x del y whole square, and then so that's all. So here we have kept it like this, okay, we have not added up. So now we can write this part as del square zeta by del x square plus del square zeta by del y square, this is whole square, minus 2, this is del square zeta by del x square into del square zeta by del y square, okay, that is this quantity, and then plus this is sigma into 1 minus sigma into this is whole square plus 2 into this is whole square. So it comes one like that. So here now this quantity and these quantities can be added. So that's what has been done over here. So finally, okay, after doing all that, so this is what we have now. After doing all this, we have this sigma plus 1 minus sigma here we added over here. So it will be 1 by 1 minus sigma, and this is 2 here. So, the 2 goes inside the bracket. So, it is 1 by 2 into 1 minus sigma, and finally, you get it like this. So, this is the elastic energy per unit volume, right. So, this is the total elastic energy per unit volume. So, this is called the elastic energy density, that we strain energy density function, okay, that we had started with, we wanted to estimate. So, this is the way to do it, and so little laborious as far as the algebra is concerned, but it is doable, and finally we get this. So, finally we get this. So, this is there. So, now we need to find out the total energy. So, the total energy will be dx dy dz. So, we have to integrate over volume. So, over here this is the z over here. So, none of these quantities depend upon z. So, therefore, we can actually integrate with respect to z here. Actually, I should say whole area, the integration over the x y we need to do. So, this signs also should be shown. So, this is E by 1 plus sigma into this is z cube by 3, z square by 3, right, and this is minus h by 2 to plus h by 2, and then we have 1 by 2 into 1 minus sigma into this is del square zeta by del x square plus del square zeta by del y square, this is whole square, and then minus whatever we have here, I am not writing everything, and dx dy. So, we have to integrate with respect to the area, surface area basically. So, over here this quantity, this is h cube by 8 minus plus h cube by 8. So, it will come out to be h cube by 8. So, h cube by 4. So, it will come out to be E, okay, and then this 2 into 1 minus sigma, that also will actually go out. Oh no, it will go out later on. Okay, this is fine. Yeah, I think this also will come out. So, it will come out to be E into this is h cube by 8. So, this is 1 plus sigma, let us say, let us leave it like that, and this is h cube by 8, it is so it is 2 into h cube by 8 actually into 3. So, because it is minus here, so it is like that, yeah, that is fine. And then over here this is 1 by 2 into 1 minus sigma into square, and then I am not writing everything here, but this you can do. So, then here it is it will come out to be E h cube by this is 4 here, 2 by 2 a by 8, 4 into 3. So, remember it is a multiplication sign. So, it is 12. So, 12, and this 1 minus sigma has to come out. So, into 2 into 1 minus sigma into 1 plus sigma, that is 1 minus sigma square actually. So, 1 minus sigma square, okay. So, E h cube by 12 into 1 minus sigma square, and then there is a half here. So, that is all it means, okay. And then this quantity will be del square zeta by del x square, and plus this is del square zeta by del y square, this is whole square, and then minus this is 2 into 1 minus sigma into this is, let us say, del square zeta by del x square into del square zeta by del y square, and then let us say I write it like this, and this is del square zeta by del x del y square, bracket close, and the whole thing is in dx dy. So, this is what we get. So, yeah, so this is the way we get it over here. So, see here this quantity is E h cube by 2 into 12 1 minus sigma square. So, this quantity E h cube by 12 into 1 minus sigma square. So, this quantity is called the flexural rigidity, okay, flexural rigidity. So, what it means? It means that how easy to bend a thin sheet. So, if if this value flexural rigidity represented by d, okay. So, if the d is small, okay, then it is easy to bend, yes, that's all it means, and if the d is large, then it will be more difficult to bend this particular plate. So, you also see that what is the unit of this? Now, E has a unit of Newton per meter square, and H is a unit of meter cube. So, the total unit is Newton meter. So, flexural rigidity has a unit of D in Newton meter. And in my last lecture, okay, where I was describing those instabilities, you possibly have noticed that I was talking about D is equal to some quantity 0.02 Newton meter and etc. Okay, I did not explain there that what this quantity D is. So, the D basically takes into account that how much is it, how difficult or easy it is to bend a thin sheet or maybe a thin rod, okay, in any item, okay, how difficult or easy it is to bend it. So, that is what is represented by this taken care of by this quantity, okay, flexural rigidity. Now, over here this energy, total energy in the film or total energy in the thin sheet is expressed by this quantity, and here it takes into account bending both about the x and y axis, because this quantity zeta, this is a function of both x and y quantity y, right. Now, what it means that, okay, we can actually use this equation, I can further simplify it in order to find out the equation, governing equation for bending of the thin plate. But to simplify our life, let us write, say that the bending occurs only about the y axis. So, let us assume, okay, that bending, okay, occurs only about the y axis, bending in y axis only. Okay. So, what it means is that this is the thin sheet, okay, and then it bends about this y axis, the y axis in this direction. So, so what it means that the z, okay, along the y axis remains same. So, this quantity z, no, zeta, okay, this is about the y axis, that remains same. So, along the y axis the zeta, so zeta varies only about the x axis. So, zeta is a function of x only, okay, zeta is no longer a function of y, because the plate is bending only about the y axis. So, therefore, here in all these cases the dependence of zeta on y is basically not there. So, all these quantities will be equal to 0. So, therefore, okay, we will have only this quantity. So, here just see what it is here is like this. Here it is half, and then we have the d, and then we have this del square zeta by del x square whole square and dx dy. So, if I see, so this is the energy. Now, here this elastic energy is because of bending. So, this is called the bending energy of the thin plate. So, this is called bending energy of the thin sheet, and this is bending energy of the total thin sheet, but then bending energy per unit area. So, per unit area, okay, will be like this, will be this will be equal to half d, and this del square z by del square zeta by del x square, that is actually curvature. So, it is actually half d curvature square, okay. So, that is all is bending energy. So, remember this, that bending energy, okay, that will depend upon that is given by half into d into curvature square. Now, you can if it is bending happening in two directions, then the curvature will be defined accordingly, right. So, you can define it accordingly and you can obtain it, you can obtain the bending energy expression, but this is per unit area. So, whenever that bending energy of the total thin sheet is to be considered, then you have to multiply it by the area. Now, if this kappa, that is the curvature, is same everywhere, then of course, it will come out, this quantity will, this del square z by del x square whole square, that will come out of this integration sign, otherwise not, okay, otherwise it will not be. You have to, if zeta depends upon the x, we have to define it like this, and here it is not depending on y, it is only up to x, because along the y axis this is same. So, here it will be half d, and then let us say it is width is w, it will be like this. So, bending energy per unit area is like, so this is what it is. Now, I will stop here today, and what I will like to do is further take this derivation further in the next lecture, and will derive the force balance equation that governs this bending of these thin sheets. Thank you.